Hello. In this video, we're going to go over a GOMC example for the Grand Canonical or GCMC ensemble using MoSDeF. My name is Brad Crawford. I would like to take the time to thank Wayne State University for support of this research and NSF under these three grant numbers, which cover GOMC and MoSDeF grants. As I previously stated, we're going to go over the Grand Canonical or GCMC ensemble. And first, to do that, we need to import the required packages, which is here. And I do want to note that box 0 is the simulated box, and box 1 is the reservoir for the simulation. What that means is box 0 is where the data is that you'll want to use when analyzing the simulation. Box 1, the reservoir, is just a place to store molecules during the simulation. It really has no data that you'd use to analyze the simulation in the end. So as I said, we import the data here, and then I'm going to set a few variables to get the box length, the total number of molecules, and the mole ratios. So we're going to specify molecule A and B, so it's a binary system. And we're going to specify box 0's length at 45 angstroms and box 1's length at 175 angstroms. And you can see I selected a different number of molecules for each box. Now, when running a GCMC simulation, you just want to make sure that there's enough molecules in box 1 so you don't run out during the simulation. For example, if you don't have enough in there and they all go to box 0 and you run out of molecules to be transferred from box 1 to box 0, the simulation will fail. So you just want to make sure your box is big enough and or you have enough molecules in there to do the simulation that you need. Some will need more molecules, some will need less. It's just very simulation specific. Molecules A and B, we're going to select a ratio of 50-50. And then we're going to select a force field variable, and we're going to select the trap UA force field, which is a standard force field that comes with MoSDeF. And you can use your own custom force fields and write your own force field files or find them from different places and tell MoSDeF how to use them. And we'll show that in later examples. And we select a force field here, and we'll just hit Shift Enter to run that. And then we move down here. So we're using the United Atom model. And what that is it just combines a bunch of atoms into a bead, minimizing the computational power that the simulation needs. Now, this is good for computational efficiency, but you also lose some information there since you only have, for example, if you use a methane, 1 bead for a methane, instead of 5, you lose a little information. So you just got to understand your benefits and losses there. But in this example, we're going to use the UA force field. And we're going to select the residues and the molecule types that we want to use. And using the UA force field, right now, I generate these mol2 files in VMD. And then I import them from this folder. So you just specify the path with the folder, and that'll get you that molecule. And I have them listed in the examples. Then we apply the force field and then rename it. This is renaming the residue pentane for pentane and HEX for hexane. And then I form a list of the molecules. So molecules A and B, and then the mole ratio list here. And then I calculate the ratio of molecules that I want for each simulation box. So it just uses the mole ratio times the total molecules, and this has to be an integer. That's why it's int there. So figure that out. You could input this directly into the function itself, but I found it easier to kind of do it step by step as you go. And it's important to know that the residue names for GOMC are treated as molecules. So each different type of molecule will need to have a different residue name. And these residue names are limited to 4 characters. I typically like to do 3 if possible. Here, I'm generating a residue name list that we'll need later. So molecule A dot name and molecule B dot name, which will print out this and this. Some of the special moves in GOMC may need to use the bead to atom dictionary. And what this does is it changes the bead name from what is standard in MoSDeF to whatever you want. So this is the standard bead name for a couple different components. So CH3, CH2, and 2 different types of CH. So what I did is I just labeled them to a carbon. So what this will do is in a hexane molecule, since there's 6 carbons, it'll just label them all C. And then since they're all C, it'll be C1, 2, 3, 4, 5, 6 in order of how it occurred. And then you can use those different names, C1 through 6, to specify for the special moves in GOMC, which they need to be uniquely named. Here we're going to build box 1 and box 0. So we just use the molecule list. So a list of the molecules, so it'd be list A and B, and then number of compounds, which are a list of 2, both being integers, and then the box dimensions. And they are divided by 10 because the standard units for MoSDeF are in nanometers. And then we do the same with box 1, only the values will be slightly different as we specified earlier. We're going to build the charm object now. So we're going to import box 0 and then name what we want to name the PDB and PSF files, import box 1, and then what is the name for the PSF and PDB files. And then here, what is the force field file name? And what is the force field file that we're going to use? And we specified earlier that it's going to be trap UA force field. And then the residues, so just a list of residues A and B. And then what the bead to atom dictionary is. And if you don't specify something in the bead to atom dictionary, it'll still give you a value, but you just won't get to choose what it is. And then do we want to fix the bonds or angles of any of these residues? And in this case, we do not. Can run that. So you can see it's building the charm object, and then it specifies what residue went to what force field. So you can see it as you go. And then it also gives you a list. Since we specified the bead to atom names, we get C for the atom names. So C1 through C5 and C1 through C6. And this gives you all the unique atom names for that residue. And then from this, we can write the force field file or IMP file, the PSF file, the PDB file, and write the GOMC control file. And what this allows us to do is automatically write the control file by using the charm object. And then what we want to name the control file, ensemble type, number of steps, temperature. And then in this case, we need to specify a chemical potential or fugacity for both residues. And in this case, I just selected a random number for the chemical potential of -4,000 and -8,000. Now, I'm not sure what these actually mean for those molecules. This isn't meant to be a full-scale simulation just to show you how it works. So you run that. We're going to go through a terminal window example of how to build the simulation files using MoSDeF and then run the simulation from the terminal. First, there is a file that is not a Jupyter Notebook. It's a Python file that's listed here. It's basically identical to the Jupyter Notebook file, except it's a Python formatted file. So we're going to copy this name. And then we're already in the Python environment that I want. You'll have to get in your own Python environment. But first we want to cd to this directory. And we can do that by also locating the file and just clicking and dragging the file in there and then deleting the file name. So we get just the directory. So there we go. So now we're located in this folder in the terminal window. And then we type Python and then we'll paste this file name in and let it run. It will take a second to run. You get some warnings because we're using beads. And then this information is shown, like I showed you before, the bead to atom dictionary that we set and some other information, the residues we used. And you can see all these files were generated, the PDB and the PSFs, and then the control file and the force field file were generated. So from here, we want to run the GOMC simulation. So we're already in this directory. So we want to pick the right GOMC binary to run. So in this folder, this is the GOMC 2.7 folder, which I'm not sure where you have that located on your computer, but if you go to the GOMC folder, you'll see a bin folder after you've built GOMC on your computer. So we'll just click on this bin folder. And then for this case, since we ran GCMC, we want to run the GOMC CPU GCMC. You can run the GPU version if that's set up on your computer or on your HPC system. But you can type this path in directly, but say you don't know how to type in the path directly, you can simply just click on this file and drag it into the terminal window, place it there, and then we want to use 2 cores for the simulation. And then we want to select the name of the control file. So we'll just copy the name. So you can copy and paste it, or you may not know, if you just type in underscore tab, it should fill in the rest of the file name, supposing there's no other files named identically to that. And we'll put the arrow, and then we'll name the log file out.date, hit enter to run. You can see the GOMC simulation started. It's already finished because it's only 100 steps, but it output the log file data here. We'll open this real quick. So you can see the log output file data and has all the information about the simulation and the steps if you run down through. And then, so it shows the steps, the last 100 step, and then the percentages that were for the simulation. And then you can also get the output from the bulk output if that's what you selected the bulk output to do. You can also select no bulk output, but standardly it's always output with bulk output unless you select it not to be. So you can see you get the density, the pressure, and some other energy variables as well. And that's pretty much it for a simple example of building a simulation using MoSDeF and running it in GOMC. Thank you. Here are the references for this video.